So let's look at the factor theorem. For any polynomial, f of x, um, x minus k is a factor of the polynomial if and only if f evaluated at k is equal to 0. So let f of x equal 3x to the fourth minus 48x squared plus 8x plus 32. Is x plus 4 a factor? Well, it is if and only if f of negative 4 is 0. So let's do synthetic division. And we see when we do it, we bring down the 3. 3 times 4 is negative 12. And we do our process. Okay. We see that we indeed get a 0 as a remainder. Since f of negative 4 is 0, then x plus 4 is a factor of f of x. So for this equation, is x plus 4 a factor? When we do synthetic division, we see we get a remainder of negative 40. So the answer is no, it's not a factor. Now, suppose I ask you to factor into linear factors, given that 5 is a 0. So I'm telling you what one of the zeros is. So what you're going to want to do is you're going to go ahead and divide by x minus 5. So do synthetic division, all right? And you see that your new polynomial is going to be 6x squared minus 7x minus 3 times x minus 5. But now we need to factor 6x squared minus 7x minus 3. All right, and we can factor that into 2x minus 3 times 3x plus 1. The rational zeros theorem tells me that if P over Q is a rational number written in lowest term, and if P over Q is a 0 of f, a polynomial function with integer coefficients P is a factor of the constant term, and Q is a factor of the leading coefficient. So the rational zeros theorem gives you only possible rational zeros. It doesn't tell you what they are. It just tells you what they possibly, it gives you a list of them. So the number of zeros of a polynomial is n. A polynomial of degree n has at most n distinct zeros. You may have some repeated zeros. So let's list all the possible rational zeros of 8x to the fourth minus 26x cubed minus 27x squared plus 11x plus 4. Turns out the only thing we care about are the first and last terms. So the factors of P are 4. So what are the factors of 4? Well, that's plus or minus 1, plus or minus 2, plus or minus 4. Nothing else divides into 4. You can do a factor tree, okay, if you like. Now, what are the factors of the leading coefficient? The factors of 8 are plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. So if I were to list all the possible zeros, it would be all of the factors of 4 divided by all of the factors of 8. So it's plus or minus 1, plus or minus 1/2, plus or minus 1/4, plus or minus 1/8, plus or minus 2, plus or minus 4. So now using our only possible rational zeros, we can find all the rational zeros of f. So let's just start with 1. Is 1 a factor? We use synthetic division, and we see that 1 is not a factor. So now we try -1. Is it possible -1 is a factor? We'll use synthetic division, and you see, yes, -1 is a factor. And so your quotient is 8, has coefficients 8, -34, 7, and 4. I can rewrite my polynomial as x plus 1 times 8x cubed minus 34x squared plus 7x plus 4. And now I can do the same process to factor this cubic polynomial. So let's start with 4. Is 4 a factor? And it turns out when I use synthetic division, indeed, it has no remainder, so 4 is a factor. So I can rewrite the polynomial as x plus 1 times x minus 4 times 8x squared minus 2x minus 1. And now I can factor 8x squared minus 2x minus 1. 2x minus 1 times 4x plus 1. So I can fully factor a higher order polynomial using the rational zeros theorem. If I wanted to find the rational zeros, you take each term and set equal to 0. So x is negative 1, 4, 1/2, and minus 1/4. Now find a polynomial function that satisfies the given conditions. Suppose I want a polynomial of degree 3 that has the zeros of negative 3, negative 2, and 5, and f of negative 1 is 6. All right. So given you have 3 zeros, then you know these are factors of f. So I know that f of x has to equal some constant times x plus 3, x plus 2, and x minus 5. Now, I want f of negative 1 to equal 6. So we can solve this for a. So I put in negative 1, and I set it equal to 6. So 6 has to equal, what is this? This is going to be 2, 1, negative 6. So 6 has to equal negative 12a. So a has to equal minus 1/2. So find a function who satisfies all this. It's going to be minus 1/2 times x plus 3 times x plus 2 times x minus 5. You can multiply that out. So let's find a function, a polynomial degree 3, that has 0 for multiplicity 3, and f of negative 2 is negative 24, or f of 2 is negative 24. So the function has the form a times x minus 4 times x minus 4 times x minus 4, or a x minus 4 cubed. So put in 2 and solve for a, and we get that a is equal to 3. So the function is 3x minus 4 cubed. Let's talk about conjugates. For any complex number, we're going to use the bar over it to mean a conjugate. So the conjugate of c plus d is a conjugate of c plus a conjugate of d. The conjugate of c times d is a conjugate of c times a conjugate of d. So basically, the conjugate of c to the n is just a conjugate of c raised to the n. Now, the conjugate zeros theorem says that if a polynomial has only real coefficients, if z is a plus bi is a 0, then a minus bi is also a 0. Remember, a conjugate, a plus bi, okay, if this is z, then the conjugate, or z bar, is a minus bi. So now remember, the polynomial has to have only real coefficients for the conjugate root theorem to apply. Otherwise, it's no longer valid. So let's find a polynomial of at least degree having only real coefficients, and the zeros are negative 4 and 3 minus I. So by the conjugate root theorem, we know that 3 plus I is also a 0, so we know we have to have a polynomial of degree 3. So the zeros are negative 4, 3 plus I, and 3 minus I. Write this as x minus negative 4, x minus 3 minus I, and x minus 3 plus I. So we need to multiply this out. Do your distribution. You get x cubed minus 2x squared plus 14x plus 40. So let's talk about the zeros of a polynomial. A polynomial with real coefficient of odd degree has to have at least one real zero. All right. A polynomial with real coefficients of even degree may have no real zeros. That's always a possibility. So let's find the zeros of x to the fourth minus x cubed minus 17x squared plus 55x minus 50, given 2 plus I is a 0. Now, since it has only real coefficients, you know 2 plus I is also a 0. So you can do synthetic division to divide by x minus 2 plus I, and you get this ugly polynomial here. All right. Now we also know that 2 minus I is a 0 by the conjugate root theorem. So when I divide through by 2 minus I, this ugly remainder theorem, I see that I have the polynomial x squared plus 3x minus 10. And this I can factor into x plus 5 times x minus 2. So the zeros are 2 plus I, 2 minus I, 5, and 2. Descartes' rule of sign says that the number of positive real zeros of f is equal to the number of variations in sign of the coefficients, or it's a number of variation minus 2 or minus 4. For the negative real zeros, you put in f of negative x and you change the number of sign, count the number of sign changes, and it is equal to that number of sign changes or less than the number of variations by a positive even number. Now, it doesn't identify the multiplicity of the zeros. So if it has exactly 2 positive real zeros, it could have 2 distinct ones, or one positive 0 with multiplicity 2. So determine the possible number of positive real zeros and negative real zeros of f of x is negative 2x to the fourth plus 3x cubed minus 5x squared plus 4x minus 1. So it has 4 changes in sign. It goes from negative to positive, positive to negative, from negative to positive, from positive to negative. So that's 4 sign changes. So it either has 4, 2, or 0 positive real numbers. 4, 2, or 0. For negative, we put in negative x. And when I simplify, I see that I have 0 sign changes because they're all negatives. So there are 0 negative roots.